We've looked at how to find the probability of a single event occurring, but now we want to start talking about the probability of multiple events. And we're going to start that investigation with this idea of the addition rule. So the addition rule, technically, if we look at its formula, is this rule here. So we say the probability of A or B. So this symbol right here, it's like a U-shaped symbol. We can interpret this to mean or. So this probability here is the probability that A or B occurs. Contrast that with this upside down U right here, which we interpret to mean and. So this probability is the probability of A and B both occurring. This symbol, the U, we call union, and this symbol we call intersection. So this is union, this is intersection. Union we can think of as or, intersection we can think of as and. So another way to write this formula is this way, where we replace the union symbol with or, and we replace the intersection symbol with and. Otherwise, these formulas are identical. We've just written the union and intersection symbols differently. Here we've used these symbols. Here we've used the words or and. But the formulas mean exactly the same thing. So either way, as we're looking through this, what we're saying is the probability that A or B occurs is equivalent to the probability of A occurring plus the probability of B occurring minus this intersectional probability, the probability that both A and B occur at the same time. Now, approaching this directly from the formula is a little confusing, but if we approach it from a real-world scenario, it actually makes a lot of sense. So let's do that now. And in order to look at this from a real-world perspective, we need to think about two different types of events, A and B. We can have the situation where the events A and B are what we call mutually exclusive or disjoint, or we can have the scenario where the events A and B are overlapping. For example, let's think about the mutually exclusive events of rolling a single six-sided die and considering the probability that we get one or an even number when we roll that die. Those are mutually exclusive events because if we think about it this way, if we have a single six-sided die and we roll it one time, and we say that event A is getting a 1 and event B is getting an even number, well, the only die roll that results in 1 is this roll right here. Rolling a 1 is the only outcome that matches event A of getting a 1 when we roll the die. But if event B is getting an even roll on the die, that could happen when we roll a 2, when we roll a 4, or when we roll a 6. So we can satisfy event A by rolling a 1. We can satisfy event B by rolling a 2, a 4, or a 6. What we want to realize here, then, is that events A and events B are mutually exclusive because they have no overlap between them. There's no overlap between these sets 1 and then separately 2, 4, and 6. If we had 1 occurring in both sets, or 2 occurring in both sets, or 4 or 6, if we had any commonality between these two sets, then events A and B would be overlapping. But here, there's no overlap between these two sets, and so events A and B are mutually exclusive. And so this example, where if we roll a six-sided die one time, and we're looking for the probability that we get either 1 or an even number, those two events there, events A and B, are mutually exclusive. They don't overlap. And so one way we can visualize that is with this Venn diagram. You may already be somewhat familiar, at least, with this idea of a Venn diagram, where we display the outcomes for any particular event within one circle in the Venn diagram. So for this particular example, if we think about this circle on the left as representing event A, which is the event that we roll a 1, and this circle on the right as representing event B, where we roll an even number, then what we can see here is that there is one outcome that matches our criteria for event A. So we would put a 1 in this event A circle. There are 3 outcomes that match our criteria for event B, and so we would put a 3 in this event B circle. We know that there are 6 possible outcomes when we roll a six-sided die one time. And so what's probably pretty intuitive to us is that the probability that we roll either a 1 or an even number is going to be 1 plus 3 divided by 6, or 4 over 6, or 2 over 3. So we have a 2/3 chance, a 2 in 3 chance, or an approximately 67% chance of rolling a 1 or an even number if we roll a 6-sided die one time. That probably feels pretty straightforward. The way that this actually applies to our addition rule formula that we started with is this way here. So we'll put it over here on the right side. We can say that the probability of event A or event B is the probability of rolling a 1 or an even number, and that is equal to the probability that event A occurs. Well, we know that that is 1 over 6 possibilities, so we would say 1 over 6, plus the probability of event B occurring, which we know is 3 over 6, so 3 over 6, and then we would subtract what we call the intersectional probability of both of these events occurring. But when we have mutually exclusive events, that intersectional probability is 0. And we see that in our Venn diagram because these circles don't overlap. In this little chart that we built, there's no overlap between the set 1 and the set 2, 4, and 6. So there's no overlap in our chart. Our circles don't overlap. There's no scenario where we can satisfy rolling a 1 and rolling an even number at the same time. There's 0 probability that event A and event B occur at the same time. It's impossible to roll both a 1 and an even number when we roll a 6-sided die one time. And so this probability is 0. So we would just subtract 0, and the result then would be 1 over 6 plus 3 over 6 is 4 over 6, or 2/3, just like we got down here when we did this intuitively. In other words, when we have mutually exclusive events, when the events are disjoint, when they have no overlap, when it's impossible for both events to occur at the same time, then this probability here, or this probability here, is 0. And so our addition rule formula simplifies to just the probability of A or B is equal to the probability of A plus the probability of B, and we completely ignore this term because it just goes to 0, and so we're subtracting 0. It has no effect on the formula. And so our addition rule formula just becomes this formula here and nothing else. That's when we have mutually exclusive events. But when we have overlapping events, so let's change the scenario here to the scenario where we roll a 6-sided die one time, and we're looking for the probability that we get a 1 or an odd number. So event A is rolling a 1, event B is rolling an odd number. If we build out our little chart here, just like we did before, what we can say is that event A rolling a 1, there's only one possible outcome there that we're interested in, and it's this outcome, rolling a 1. This is here event A, and this is event B. Okay, but then rolling an odd number, we'll roll an odd number if we roll either a 1, a 3, or a 5, because those are the odd numbers on our 6-sided die. And what we see right away is that we have an overlap for the first time. We have the overlap of 1 in both sets here. So set A is just 1. Set B is 1, 3, and 5. So we have this overlapping value of 1 in both sets A and B. And that makes sense because 1 is an odd number. So we can satisfy event A by rolling a 1. We can satisfy event B by rolling a 1, 3, or 5, and 1 occurs in both sets, which means that this intersectional probability, the probability of A and B both occurring, is non-zero. Our events are overlapping. There is some probability, of course, that we could roll a 1 and an odd number because 1 itself is an odd number. When we have overlapping probability like this, when we have overlap in our table, when our intersectional probability is non-zero, then in our Venn diagram, we have overlapping circles. And this overlapping portion in the center here, the overlapping part of the circles, represents that overlap. So if we label this left circle again as event A occurring being a 1, and this right side circle as event B being an odd number, then we need to treat each of the 3 sections of our Venn diagram very carefully. So this section on the left here, the section that is inside circle A here, but completely outside of circle B, So just this little moon-shaped section over here on the left, this section represents all of the possibilities where we roll a 1, but not an odd number. Think back to when we talked about complementary probability. This right side circle represents all of the odd numbers. So when we're outside of this right side circle, we're completely outside of the odd circle, and we're just in this little left-hand portion here. These are all the outcomes where event A occurs, but event B definitely does not occur. So this left side here is A, not B. This right side is B, not A. And the middle is A and B. So if we're thinking about the left side as A, not B, then we're saying all of the outcomes where we roll a 1, but not an odd number. But of course that's 0, because it's impossible to roll a 1 and not an odd number. 1 is itself an odd number, so if we were to roll a 1, by definition, we also roll an odd number. So this has to be 0, because there's literally no way to roll a 1 and not an odd number. So this section over here of A, not B, contains 0 possibilities. On the right-hand side here, this is B, not A. So the probability that we roll an odd number, but not a 1, is 2. Because if we go back to our chart here, there are 3 ways we can roll an odd number, 1, 3, and 5. But if we want an odd number and not a 1, we can't include this 1 value in our set 1, 3, and 5. So the only way to satisfy B and not A, or an odd number and not 1, is with a 3 or a 5. So there's 2 possibilities. So we put 2 over here. And then in the center, this is A and B both occurring. So how many ways are there to get a 1 and an odd number? Well, there's only one way, because there's only one way to get a 1, but 1 is itself an odd number. So there's exactly one and only one way that we can roll a 1 and an odd number, and that is to roll a 1 itself. So we fill in our Venn diagram. And then if we want to use this Venn diagram to determine the probability that A or B occurs, going back to our addition rule formula, we want the probability of A or B, the probability of A or B. All we have to do is follow the formula and look at the probability of A. Well, the probability of A, if we look at the entire circle of A here, there's one possibility that A occurs. In other words, we add up all of the values that are inside the circle A. So 0 plus 1 or 1, there's one possibility that A occurs. We know there's 6 total possibilities when we roll a 6-sided die one time. So the probability of A occurring is 1 over 6. The probability of event B occurring, we add up all the values inside the circle B. That's 1 plus 2 or 3. So we say plus 3 over 6. But then we subtract this intersectional probability. That means subtracting the intersection of the Venn diagram. And inside the intersection here, we have this value of 1. So we subtract 1 over 6, and we get 1 over 6 plus 3 over 6 minus 1 over 6, or 1 plus 3 minus 1, all over 6, is equal to 3 over 6, or 1/2. So the probability of A or B occurring in this scenario is 1/2. The probability of rolling a 1 or an odd number is 1/2. And that makes sense because when we look back at our chart here, the probability that we get a 1 or an odd number, just intuitively, is going to be satisfied when we roll a 1 or a 3 or a 5, which is exactly half of the possibilities when we roll the 6-sided die one time. So specifically, plugging into this addition rule formula here, the probability of getting a 1 or an odd number is 1 over 6 plus 3 over 6 minus, and then instead of our intersectional probability being 0, like it always is with mutually exclusive events, when we have overlapping events, we subtract the intersection, which in our case is 1 over 6. So we get minus 1 over 6 is equal to 1 plus 3 minus 1 over 6, or 3 over 6. 3 over 6 is equal to 1/2. And so the probability of getting a 1 or an odd number is 1/2. The other way we can calculate this probability when we have overlapping events is just to add up all the numbers in our Venn diagram. So we can just add 0 plus 1 plus 2 to get 3. 3 is our number of matching events. We divide that by 6, the number of total events. And so we get 3/6 or 1/2 the same value we got here. In other words, two ways to calculate the probability here. If we've built out the Venn diagram, we can just add all the numbers in the Venn diagram. 0 plus 1 plus 2 is 3. 3 divided by 6, we get our probability of 1/2. Or we can add up all the values in circle A to get the probability of A, add up all the values in circle B to get the probability of B, and then subtract out the intersectional probability to eliminate that overlap, and we'll get to the same answer, 3/6 or 1/2, 50% chance of rolling a 1 or an odd number. So again, the whole idea here with this addition rule and this union versus intersection concept is just that we have to pay special attention to or be careful with this intersectional probability right here. Because when we're calculating the probability of one event or another occurring, we don't want to double count events that occur in both sets. Over here, with this overlapping probability, one occurred in both set A and set B. And so if we don't subtract out this intersectional probability, if we don't subtract out this value, we will double count it as part of event A and part of event B, and we'll overstate our probability. Going back to our chart here, if we just say that the probability of event A is 1/6, so this event right here is 1/6, and the probability of event B is 3/6, 1, 2, 3, matching outcomes divided by 6 possible outcomes, so plus 3/6. And we just add those two probabilities together, we get 4/6 or 2/3 or a 67% chance that we get 1 or an odd number. But of course, we know already that that's not true. The probability of getting 1 or an odd number is 1/2, it's 50%, not 2/3 or 67%. This calculation, where we just add the two individual probabilities together, double counts this value of 1 in both probabilities, and so we overstate the probability. We have to account for the fact that 1 occurs in both sets, and we need to make sure that we don't double count it, and instead that we only count it one time, eliminating the overlap here, or taking out that intersectional probability where we subtract out the probability of A and B occurring. We subtract out the probability of A and B occurring. We eliminate that double counting, and we end up with an actually accurate probability for this scenario of overlapping events. So that's how we use the addition rule to calculate the probability that event A or event B occurs, by using this concept of union and intersection and translating that into this visual idea of the Venn diagram, where we can clearly show mutually exclusive events with non-overlapping circles, or overlapping events with these overlapping circles in our Venn diagram.